Hello dear students, you are all most welcome to today's chemistry class in this EduSat educational channel. Today we are going to discuss the very important and a most exciting topic in inorganic chemistry. Do you know the topic? Yes, it is a D-block elements, that is transition metals. This topic is very important from examination point of view, from entrance point of view, and what I have noticed, this topic is least liked by many students. Yes, is not it true? But today I will clear all your doubts, all your fears, everything from your mind. बस बैठ जाइए, अपना कॉपी लेके, पेन निकालिए, लिखते जाइए, मैं बोलता जा रहा हूँ, ठीक है? So today's topic is D-block elements, that is transition elements. So before going into discuss in detail about the topic, let us have a look into the things to be discussed in today's class, right? So first I will discuss about introduction. What is introduction? Means a definition. It will include your classification, position of a D block in the periodic table. We'll discuss in detail. Then we'll discuss electronic configuration and a metallic character. Next is your atomic size, ionization energy or ionization enthalpy, and a last one is your oxidation states. There are many properties, but I will try to complete this topic in 2 classes. Okay. So let us discuss about the D block elements, its position in the periodic table, right? You know, in the periodic table, I am just making a block diagram of a periodic table. So this is your periodic table. You must have seen. This is your periodic table. This is your periodic table, right? So this is your S block. It contains 2 groups, group 1, group 2, alkali metal and alkaline earth metals. At the right hand side, you have 6 groups called as P block. So it contains 6 groups, 13, 14, 15, 16, 17 and 18. In between this S block and P block, your D block is located, right? So this D block contains, you see, it contains group number 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So that means these 10 groups from group 2 to group 13 are coming under D block category. Its position is in the middle, in between S block and P block. S block elements, you know, they are highly electropositive. They are highly electropositive, they love to donate the electron and become positive charge, right? The P block elements, you know, they are electronegative, means they love to take electrons because of their electron affinity, electronegativity character. They love to take electrons. These S block elements, they love to donate electrons, electropositive, electronegative. In between these 2 extreme groups, here comes transition or D block. So D block contains 10 groups and there are 4 series. These are D block elements. These are called as transition elements. Why they are called as transition elements? So many times this has been asked in the examination. What are transition elements? D block elements are called as transition elements. They are called so because there are 3 reasons. There are 3 reasons why they are called as transition elements. Number 1, their position is in between S block and P block. Electropositive, electronegative, means the properties are almost intermediate. Transition means a change. When you move from electropositive character element to electronegative character elements, you must see some changes in properties. That changes is called as transition means the properties are intermediate between the electropositive S block and a P block, number 1. Number 2, the valency cell, the outermost cell and the nearest inner cell both are incomplete. Both are incomplete. The valency cell and the nearest inner cell means a penultimate cell, both are incomplete. Here comes a question, how come the inner cells are incomplete? How the electron moves to outermost cell? Yes, I will discuss about this in electronic configuration. Second property. Third character is they must have partially filled d orbitals. Matlab, they cannot have a D0, you know the D subcell has capacity, maximum capacity that it can accommodate 10 electrons. So, it cannot have a D0 configuration and a D10 configuration. जिस एलिमेंट के पास ये कॉन्फ़िगरेशन है वो कभी ट्रांजिशन एलिमेंट से नहीं हो सकते हैं. ये दोनों कंडीशंस नहीं होना चाहिए. मीन्स दे हैव D1 to D9 कॉन्फ़िगरेशन. D सबसेल में थोड़ा बहुत वैकेंसी होना जरूरी है. So these are the 3 reasons why they are called as transition elements. Number 1, properties are intermediate between S block and P block elements. Number 2, their valency cell and nearest inner cell both are incomplete and they have partially filled d orbitals, right? If this is true, you see, you have here zinc, cadmium, mercury. You must have heard these names. Zinc, in case of zinc, you have 3d10 and a 4s2 configuration. In case of cadmium, you have 4d10 and a 5s2 configuration. And mercury, it is 5d10. So these elements have d10 configuration, means they have fully filled d orbitals. Can we call them as a transition metal? Can you call them as transition metal? Because yes. What is your answer? No. They do not fulfill this criteria because they contain 10 electrons in their d subcell. So they are not called as transition elements. Even their stable oxidation state, in their stable oxidation state, they also contains d10 electrons. So as per the definition, they must have to have partially filled d orbitals, लेकिन उनके पास d10 कन्फिग्रेशन है. 10 की 10 इलेक्ट्रॉन्स डी सबसेल में, सारी की सारी डी सबसेल भरा पड़ा है, इसलिए उनको ट्रांजिशन एलिमेंट्स नहीं कह सकते हैं. रादर दे आर कॉल्ड एज डी ब्लॉक एलिमेंट्स. दे belong to D block, but they are not transition metals. That means all D block elements are not called as transition elements, but transition elements belong to D block. ये बात ध्यान रहे. So they are other called as typical transition elements. They are called as typical transition elements. You can call them as typical transition elements. So the transition elements are divided into 4 series. They are divided into 4 series. 4 series, you see, first transition series, this is your first transition series, this is your second transition series, third transition series and fourth transition series. First transition series starts with this scandium 21 and continues to till zinc 30. It contains 10 elements. Second transition series starts from yttrium 39 and proceeds up to cadmium 48. Third starts from lanthanum 57, then comes 14 elements called as lanthanides in between, then you start with hafnium 72 and then it proceeds up to mercury 80. So from hafnium 72, mercury 80, there are 9 elements and lanthanum is 110 again. And this is here actinum starts with actinum 89 and in between these, here you have lawrencium 104, in between actinum and lawrencium, your comes 14 elements as actinoids. Then from lawrencium to ununbium, UUB 112. These 9 elements plus actinum, again there are 10 D block elements. So this fourth transition series, it is called as 6D series. this is called as 5D series, this is called as 4D series, and this is called as 3D series. So total 4 into 10 means there are 40 elements all total. But these extreme, the 12 group elements like zinc, cadmium, mercury are not pure transition elements. They are rather called as typical transition elements, and they are the members of only D block, right? Let us discuss about the general electronic configuration or the electronic configuration of all the elements. This is very, very important. I will tell you a trick how to remember all these elements. So these are the, let us discuss about electronic configuration. So these are the elements, atomic number, and how to write electronic configuration. The elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. How to remember? How to remember these elements? Here is a trick. Here is a mnemonic in Odia. Yes, I have developed this mnemonic. Very interesting. How to remember? Scooty re Bikrama, Scooty re Bikrama, Ferry, Scooty re Bikrama, Ferry, कोणार्क निकटरे कूओ को जंप कला सुइछड़ी किया उन्होंने याद रहा स्कूटी रे स्कूटी मीन्स स्कैंडियम टिटानियम विक्रम VCRMN विक्रम फेरी कोणार्क निकटरे कूओ को जंप कला atomic number it is 21, it is 22, 23, 24, 25, 26, this is 25, 27, 28, 29, 30. You will ask to write electronic configuration of an element, but you will not be given the atomic number. How to remember the atomic number? Here is a trick. Suppose you are asked to write down the electronic configuration of a copper. Okay? You are asked to write down the electronic configuration of copper, but you are not given the atomic number. How will you remember what is the atomic number? You just remember the mnemonic. Scooty re Bikrama Ferry Konarka Nikatare Kuoku. Means its number is 9. If any element comes at number 9, means its atomic number is 29. If its number comes at 6, 26. If its number comes at 5, it will be 25. Okay? So what are the electronic configuration? It is 1s2, 2s2, 2p6, 3s2, 3p6. Instead of writing all these things, I can write as argon, then your 4s2, 3d1. So similarly, it is argon, 4s2, 3d2, 4s2, argon, 3d3. In case of chromium, it is 4s1, 3d5, not 4s2, 3d4. It is not like that. In case of manganese, you have argon 4s2, 3d5, iron 4s2, argon configuration 4s2, 3d6, cobalt 4s2, 3d7, 28 4s2, 3d8, copper 4s1, 3d10. So it is the exceptional electronic configuration of a copper and a chromium. You will be asked a question on this 4s2, 3d10, right? So the general electronic configuration you see is n-1 d 1 to 10 and ns 1 to 2. Here comes a question. Why the electron is filled in 4s orbital, fourth cell is valence cell. Electron is supposed to be filled in a 3d subcell, but electron is filled in a 4s subcell first, then 3d. Why? It is because there is a rule called as n plus L rule. That n plus L rule decides to which subcell electron will be filled first. between 4s and 3d, that you must have read it in the above principle. You must have read it in above principle. Its n value equal to 4 and L equal to 0 for S subcell. It is L equal to 0, so n plus L equal to 4. Here n equal to 3, L equal to 2, so n plus L equal to 5. So 4s has a lower n plus L value, so it possesses lower energy and is filled fast. So that is why in all cases 4s subcells are filled fast than 3d. Okay? But in case of a chromium and a copper, this is a special configuration, exceptional case, because the energy difference between 4s and 3d, 3d and 4s के बीच में एनर्जी डिफरेंस है ना बहुत ही कम है. सो इसलिए इलेक्ट्रॉन मूव्स फ्रॉम 4s to 3d4 and makes it half filled. Both are half filled, and that they, because of their half filled, they gain stability. Similarly, in case of a copper, electron moves from 4s to 3d and makes it fully filled. That is why they are exceptionally stable and they get extra stability. Okay. Now you must have clear why 4s subcell is filled fast than 3d. It is the n plus L rule that determines, that decides which subcell is to be filled fast and next. If it is true, you see here is a confusion, here is a contradiction. We know the subcell or the cell to which last electron enters is supposed to be the valence cell. If electron enters into D subcell at last, so this should be the valence cell. And if ionization processes takes place, if electron is excited, then it must go from that cell in which it is filled at last. है ना नहीं? जिस सेल में या सब सेल में इलेक्ट्रॉन लास्ट में एंट्री करती है तो उसी से वो जाना चाहिए, वो वैलेंस सेल होना चाहिए, लेकिन यहाँ नहीं हो रहा है. तो इलेक्ट्रॉन मीन्स एट लास्ट इट इज फील्ड इन डी सब सेल, बट व्हेन आयोनाइजेशन टेक्स प्लेस इलेक्ट्रॉन goes from 4s subcell. For example, if you are asked to write down the electronic configuration of a ferrous, what will be your answer? Many students are doing mistakes. Many students are doing mistake. What mistake they are doing? They simply write atomic number is 26. 2 plus means it loses 2 electrons, means it has a 24 electrons. At 24 electrons, they do the electronic configuration like a chromium. It is suicidal. ये आत्मघाती है. ऐसा नहीं करना चाहिए. Like, how will you write down the electronic configuration of a cation? You have to write down the electronic configuration of its atom first. Here it is atom. Argon 4s2 3d6. अभी इलेक्ट्रॉन जो जाएगी वो 3d से नहीं 4s से जाने वाली है. Because 4s is the valence cell, 3d is not valence cell. Although electron is filled here at last, it is not valence cell. One reason is effective nuclear charge. Effective nuclear charge of a 3d subcell is greater than 4s, means the nucleus की जो होल्ड है, जो पकड़ है, वो 3d subcell से ज़्यादा है. So इसलिए these electrons will not let these electrons to go out. Rather 4s orbital electrons will be removed because its effective nuclear charge is lower than that of a 3d subcell. So ठीक है. Now you must be clear, when electron filling की बात आएगी n plus L rule dominates. When electron जाने की बात आएगी तो effective nuclear charge dominates, right? So next is your metallic character. You know, metallic character, all transition elements are metals, hard metals except mercury. Except mercury, all are solids, hard solids, because of strong metallic bond present in between its structure, between the atoms, strong metallic bond, so they are hard and brittle. Also, they are also malleable and ductile. As you know, these are the characteristic property of metals. So transition metals have similar properties of all the metals. And they are also good conductor of heat and electricity. And among the transition metals, copper, silver, gold. Copper, silver, gold are very good conductors of heat and electricity. And in their metal structure, they have hexagonal close packing or BCC, body centered cubic packing, or they may have FCC structure. They may have FCC structure or BCC structure, or they may have HCP structure or lattice. Next comes your atomic size. You know, if you compare the atomic size of S block and P block with D block, in S block and P block there is a regular trend in atomic size. Atomic size gradually decreases, may it be covalent radius, smoothly it decreases. But in case of transition metals, of course, size decreases, but the variation is very irregular. In some portion it decreases, in some portion it remains same, and in some portion it increases. There is no regular variation. Overall, if you look from scandium to zinc, there is a slight decrease in atomic size, but that trend is not as much as in P block. So, there is a decrease in atomic size, change in atomic size, but there is no regular trend. It is because you see here effective nuclear charge plays again important role. Remember one trick, the effective nuclear charge of transition elements increase with this order 2.85 plus 0.15 into n. Remember this formula, very important. N means the number of d electrons, n means the number of d electrons. If effective nuclear charge increases, so the valence electrons will be strongly attracted towards the nucleus. You see, in case of scandium, you have only one d electron, n is 1, and in case of titanium 2, n is 2, and in this way if you put the different values of n, you see the effective nuclear charge gradually increases from scandium to zinc. So, size should decrease. So, size should decrease, but size does not decrease from starting to end, because you see from scandium to manganese, size decreases smoothly, no problem. But from iron to copper, size remains almost constant, then towards the end size increases. Size initially decreases up to manganese, then almost remains constant up to copper, and towards zinc it again increases. Why? Up to manganese you see you have D5 configuration, means exactly half filled and fully filled, exactly half filled configuration, exactly half filled means minimum repulsion. And after manganese in iron you see D6, iron has D6 means you see D6 means D6 means D5, each d orbital contains 1 electron and 1 d subshell is now paired up. Effective nuclear charge increases at the same time because of pairing starts after iron, after manganese with the iron, pairing of electron starts. Pairing means repulsion. So, attraction increases, repulsion increases. Attraction brings the valence shell closer and repulsion makes it to move away. So, they cancel each other. Attraction and repulsion cancel each other. So, size remains constant up to copper. So, here up to repulsion, electronic repulsion and effective nuclear charge are balanced. Now, towards the end zinc, since all the d subshells are fully filled, so zinc there is a greater repulsion, greater attraction, but greater repulsion. So, repulsion dominates over effective nuclear charge. Repulsion dominates over effective nuclear charge, that is why zinc has a little bit higher atomic size than copper. Oh, what is the overall size? What is the overall size among the transition metals? Very important to remember. I will also give you a trick. Here scandium, titanium, manganese, zinc, manganese greater than vanadium, greater than chromium, nearly equal to copper, greater than iron, cobalt nearly equal to copper. How will you remember? स्कूटी में जिंक के साथ मैंगानीज, स्कूटी में जिंक के साथ मैंगानीज, देखो the atomic size of atomic size decreases, देखो so scandium has a higher atomic size, titanium then comes zinc again increases, so zinc has a higher atomic size, zinc के साथ मैंगानीज ये दोनों का atomic size बराबर है, then they are more in size than vanadium, and copper and chromium has almost similar size, copper and chromium have almost a similar size, then iron, cobalt and sorry this is nickel, so this is nickel, they have similar atomic size, but their size is the lowest among 3D elements. Okay? So the size you see there is no regular trend, we see it decreases but not regularly, somewhere it is higher, somewhere it is lower and somewhere it does not change. ये तो बड़ी खासियत बात है और ये स्पेशल कैरेक्टर है फॉर टेंशन एलिमेंट्स. ओके, नेक्स्ट प्रॉपर्टी विल डिस्कस इज ऑल्सो वेरी वेरी इंपॉर्टेंट प्रॉपर्टी बिकॉज मेनी अदर प्रॉपर्टीज डिपेंड्स अपॉन दिस characteristics value, that is ionization energy or ionization enthalpy of transition metals. You know ionization energy, what is ionization energy? It is the minimum amount of energy required to remove the most loosely bound electron from the outermost cell of an isolated gaseous atom. That is the first ionization energy. Similarly, the energy required to remove the second electron, third electron, fourth and so on are called as successive ionization energies, and you know successive ionization energy gradually increases. Here in case of ionization energy, when we are talking of ionization energy of transition metals, again we see there is irregularity. ये ट्रांजिशन एलिमेंट की बात है, इनके जो प्रॉपर्टीज है बिहेवियर है थोड़ा अलग है एस ब्लॉक और पी ब्लॉक से. थोड़ा ध्यान से उसको समझना, ये बात को समझना और जानना बहुत ही जरूरी है. व्हाई ऑल दिस हैपेंस? यू सी लाइक atomic size gradually decreases up to manganese, then remains constant and towards the end increases. But here ionization energy gradually increases from scandium to manganese because effective nuclear charge gradually increases with this formula 2.85 plus 0.15 into n. As effective nuclear charge gradually increases, the force of attraction between nucleus and valence shell electron gradually increases. So obviously more and more energy will be required to remove the electrons. ये कहानी manganese तक सही है. After manganese the problem starts because after manganese pairing of electrons starts in d subshell and that pairing causes repulsion. So attraction, effective nuclear charge attraction and the repulsion, electronic repulsion, they balance each other. Again ionization energy almost remains constant. Again ionization energy remains constant. But towards the end, between copper and zinc, so many times it has been asked in competitive examinations between copper and zinc. Zinc has a larger size, so it should have a lower ionization energy compared to copper. But ऐसा नहीं है. The ionization energy of zinc is greater than copper. The ionization energy of zinc is greater than copper. Here size not dominates. It is the stability of electronic configuration. You see in zinc, you have 4s2 3d10 means 4s subshell is fully filled and zinc and 3d is also fully filled. Because of a fully filled orbital, it gains extra stability, and because of that extra stability, its ionization energy is higher than that of a copper, right. So from scandium to manganese, it gradually increases due to increase in effective nuclear charge, then almost remains constant up to copper, and then ionization energy of a zinc increases because of extra stability due to fully filled configuration. Clear? You see, if you look into the general trend of ionization energy among 3D elements, here is a sequence order. This is very very important for your entrance examination point of view. The the ionization energy variation among 3D series elements is like this. Here is a mnemonic. Here is a mnemonic to remember. I am just telling you that mnemonic to remember. न जाने फिर कोमल क्यों नहीं मानती कि वो भी कर सकती है. Means the ionization energy of zinc is greater than iron, greater than cobalt, greater than copper, greater than nickel, greater than manganese, greater than titanium, greater than vanadium, greater than chromium, and your scandium has lowest ionization energy or lowest ionization enthalpy. Here, how to remember? न जाने फिर कोमल क्यों नहीं मानती कि वो भी कर सकती है, वो भी सक्सेस हो सकती है, वो भी नीट और IIT कुछ भी क्रैक कर सकते. इसी तरह से उसको भी you can remember this mnemonic. Very, very interesting. So chemistry is full of all tricks and tips. You see, so this is how the ionization energy varies among 3D elements. Okay. Next, if you look into the group, scandium group, scandium, here is your titanium, vanadium, chromium, these are the different groups. But if you move down the group, the ionization energy in the scandium group, ionization energy decreases in the scandium group. That is 3D, the ionization energy of a 3D greater than 4D, greater than 5D. Remember this only for scandium. But in case of titanium, vanadium, chromium and nickel, remember these tricks. These are very important tricks. In case of titanium, vanadium, chromium and nickel, the ionization energy gradually increases. Ionization energy gradually increases. Here it decreases. Here in these 4 groups only, the ionization energy gradually increases down the group, because there are many factors out of which your lanthanide contraction dominates, comes into play here. But I am not going to touch upon that part. Okay. So just remember, I am telling you the tricks how to remember. So in case of a scandium group, the ionization energy down the group decreases, and in case of titanium, vanadium, chromium and nickel, the ionization energy gradually increases. That is, in this case 5D has a greater ionization energy than 4D, greater than 3D. Right? The remaining 5 groups, the rest 5 groups, you just remember the trick, the tick mark. The remaining 5 groups means scandium, titanium, vanadium, chromium, manganese, iron, cobalt, copper, zinc. Manganese, iron, cobalt, copper and zinc. In these 5 groups, how the ionization energy varies down the group, remember this tick mark. Tick means this is 3D, this is 4D, this is energy, and this is your 5D. So that is 5D has greater energy than 3D and than 4D. Only for these 5 groups. This is for your entrance point of view. Remember, this is very, very important trick. So ionization energy of scandium group decreases down the group, and in case of titanium, vanadium, chromium and nickel increases, but in remaining just remember the tick mark. That means 5D has a higher ionization energy than 3D than 4D. Right? Next is the oxidation state. Transition metals, it is very, very important character, important property. Transition metals show variable oxidation states. Variable oxidation states, variety of oxidation states, because of participation of both s orbital and d orbital electrons in bonding. 4s के साथ साथ 3d इलेक्ट्रॉन्स जब बॉन्डिंग में पार्टिसिपेट कर रहे हैं एक के बाद एक, इसीलिए तो द ऑक्सीडेशन स्टेट ग्रेजुअली इंक्रीजेस. रिमेंबर दे हैव 4s, दिस इज वैलेंसी सेल, this is valence cell, this is penultimate cell, this is penultimate cell, this is penultimate cell, but the 4s 2 electrons they participate. So they show oxidation state of +2. Minimum is +2 because when 4s2 electrons participate in bonding. Only when 2 electrons of 4s subshell participate in bonding, because of being valence shell, it shows +2 oxidation state minimum. And after that, when 1 or more d orbital electrons participate in bonding with the 4s orbital, then they start showing more number of oxidation states. Now question comes, why 3d orbital electrons participate in bonding along with the 4s orbital? It is only reason is the energy difference between energy of a 3d subshell is nearly equal to energy of a 4s subshell. Means the delta E is very small, very small. That is why the 3d orbital electrons participate one after another in bonding along with the 4s orbital. So therefore it shows variable oxidation state. And let me write down here the different oxidation states shown by these elements. Scandium shows your +2 and a +3, titanium +2, +3, +4, vanadium +2, +3, +4, just increase one by one. Then chromium +2, +3, +4, +5 and +6, +2, +3, +4, +5, +6 and +7. Here iron +2, +3, +4, +5, +6 highest, but these are unstable. Cobalt +2, +3, +4, nickel +2, +3, +4, +3 is unstable, copper is +1 and maximum is +2, and zinc has only +2. So you see what happens here in the oxidation states. Scandium shows a +2, means all shows +2 only when 4s orbital electrons participate. 2 electrons of 4s orbital participates in bonding. When d orbital electron participates, it becomes +3. So because of participation of a d orbital electron, the oxidation states increases. And you see, as the number of d orbital electrons gradually increases up to manganese, you see manganese, then pairing of electrons starts here. The maximum number of d orbitals participating in bonding is 5 + 2, 7. So it shows the maximum oxidation state. So manganese shows maximum oxidation state among 3d series. Okay? So this oxidation state is unstable. And in case of titanium, you see it shows +2, +3, +4. Vanadium, you see, vanadium also shows oxidation state +2, +3, +4 and +5. But chromium +4, +5. In case of chromium, these are unstable oxidation states. I am enclosing in a bracket. These compounds cannot exist. They are highly unstable. Iron, of course, of +4, +5. It can show these oxidation states, but these compounds cannot exist in this oxidation state, right? And in case of cobalt, you have +2, +3, +4, +5. So these are highly unstable. And in case of nickel, it is +2, +3, +4, +3 is unstable, and the remaining oxidation states of copper and zinc are stable. Remember one thing, very important thing. The lowest oxidation state is due to participation of 4s2 electrons. Highest oxidation state is due to participation of ns electrons plus n-1 d electrons. Due to participation of ns electrons and n-1 d electrons. So here the ns2 along with the n-1 d electrons, it shows the highest oxidation state. So manganese shows the highest oxidation state of +7. But among transition metals, among all transition metals, you see there are 4 series, first, second, third and fourth series. You see the highest oxidation state is shown by osmonium and ruthenium. Osmonium and ruthenium +8. उससे भी ज़्यादा दिखाते हैं. What are the important properties shown by these transition metals at these oxidation states, right? You see, at the lowest oxidation state, lowest oxidation state oxidation state, it forms ionic compound. Ionic compound, for example, manganese oxide MnO, its oxidation state is +2, it is ionic. And in highest oxidation state or higher oxidation states जैसे जैसे increase करती जाएगी तो covalent compounds are formed. Covalent compounds are formed. So Mn2O7 is covalent. That means with increase in oxidation state, the covalent character increases. Next, your nature of oxide. When oxidation state very important. If oxidation state is less than equal to 2, the oxides are metal oxides are basic. If oxidation states are greater than equal to 3, then metal oxides are acidic. Remember these things. For example, manganese oxide, oxidation state is +2, it is basic. But Mn2O3 and MnO2, you know they are amphoteric. Amphoteric means partly acidic and partly basic. But if you go to higher state, Mn2O6, Mn2O7, here oxidation state is +6, +7, so they are acidic. So that is with the increase in oxidation state, acidic character increases. And at a highest oxidation state, one element shows oxidation character, and at lowest oxidation state, one shows reducing character. Remember these very important points. So chromium, manganese, you know, at the highest oxidation state, it is potassium permanganate shows oxidation character, and chromium also shows oxidation character at its highest oxidation state of +6. Are you clear about the different oxidation states shown by transition metals? Hope ये सारी कहानी आप लोगों की समझ में आ चुका होगा. फिर भी बता देता हूँ, रिपीट करता हूँ. So you see the transition metals show variable oxidation state because of participation of both N-1 d and Ns orbital electrons in bonding because of a very close energy difference between these two orbitals. And the oxidation state gradually increases up to manganese, then decreases up to zinc. The lowest oxidation state is shown by copper, that is cuprous, +1, that is cuprous. And the only one oxidation state is shown by zinc. Remember this one. And the +2 is the most common oxidation state shown by all the transition metals, particularly 3D elements. And highest is shown by manganese, and at highest oxidation state, one element shows its oxidation character. That is why potassium permanganate, where oxidation state of manganese is +7, is a very strong oxidizing agent. Both in acid medium, in alkali medium, and in neutral medium, you have already read it in your first year class. So similarly, chromium shows the maximum oxidation state of +6, hence potassium dichromate, chromic acid, all are very good strong oxidizing agents. And at lower oxidation state, they show reducing character. At lower oxidation state, they form ionic compound, and at a higher oxidation state, they form covalent compound. And at a lower oxidation state, their oxides are basic, and at a higher oxidation states, their oxides are acidic, and in between, there may be some amphoteric in case of manganese. So these are the basic characters exhibited by the transition metals at different oxidation states. Ferrous, ferric. You see, ferrous and ferric. If you compare the stability, now let us discuss about the stability of oxidation state. Which oxidation state is more stable and which is less stable? How will you explain it? There are many factors. One factor is your electronic configuration. Electronic configuration, you remember, if you see any electronic configuration, that has, remember these tricks, these points, any electronic configuration in which the metal cation has D0 configuration or D5 configuration or D10 configuration, are supposed to be more stable, because in D0 configuration means it has almost argon configuration. D5 means exactly half filled configuration, and you know exactly half filled configuration, the elements are more stable. And this is the fully filled orbital. Fully filled orbitals are more stable. So any cation or element at any oxidation state, if it has any of these following configuration, that means they are more stable. So many times it has been asked in the examination between ferrous and ferric. Ferrous and ferric, which ion is more stable? Which ion is more stable? In ferrous, you see iron 26, argon 18. How to write? 4s2, 3d6, right? In Fe2 plus means you have to remove these 2 electrons. That means argon 18 and 3d6. 3d6 means you have, you see, now fill up the d orbitals. 1, 1, 1, there are 5, all the d orbitals are now singly occupied, and this is a pairing. So here it is not exactly half filled. In case of a ferric, so you have argon and 3d5. 3d5 means you have exactly half filled orbitals. Exactly half filled orbitals, you know exactly half filled orbital means minimum electronic repulsion, greater exchange energy. That is why ferric ion is more stable than ferrous. So it is one of the criteria. That is why the atom at a particular oxidation state is more stable. But it is not the sole criteria. वो एक ही region नहीं है. There are many other regions that provides stability to a particular oxidation state. If ferric is only stable, then iron should not exist in ferrous state. But ferrous is also more stable. So stability depends upon many factors like enthalpy of atomization, ionization enthalpy, and your enthalpy of a solution. These are the factors. Enthalpy of atomization, how much energy is required to convert that metal to gaseous atom, that is called enthalpy of atomization. Ionization energy and also your enthalpy of solution means in toto it is called standard reduction potential. Standard reduction potential is your sublimation energy plus ionization energy minus enthalpy of a solution. If SRB, standard reduction potential of a particular oxidation state, remember this fundamental trick. If SRP is negative, that means that ion is stable. शायद ये बात आप लोगों की समझ में आ गया होगा. That means to become this negative value, sublimation energy should be low. ये low होना चाहिए और ये भी low होना चाहिए, तब कि ये negative होगा. Negative होगा means stable. So stability depends upon so many factors, but electronic configuration is not the sole criteria. And let me explain one more beautiful thing here. Ionization energy also explains the stability. Ionization energy also explains the stability of different oxidation states, like for example nickel 2 plus and platinum 2 plus. Between these two cations, which is more stable? In case of nickel you give first ionization energy, it becomes Ni plus, then you give first second ionization energy and it becomes Ni2 plus. In case of platinum, similarly ionization energy 1, Pt plus, ionization energy 2, it becomes Pt double plus. So if in case of nickel, the ionization energy 1 and ionization energy 2 of nickel is less than ionization energy 1 and ionization energy 2 of platinum. So sum of ionization energy of nickel is lower than that of platinum, hence nickel cation is more stable than platinum. But in case of Ni plus 4, Ni4 plus and a Pt4 plus, here if you see ionization energy 1 plus ionization energy 2, 2 plus ionization energy 3 plus ionization energy 4 of Pt is less than 4 ionization energies of Ni. Hence, Pt 4 plus is more stable than Ni 4 plus. Means if sum of ionization energy of a particular cation is low, then it is more stable. Okay? Next, we will discuss about some previously asked questions. So many times it has been asked what is the electronic configuration of chromium and a copper. If electronic configuration will be asked, it will be only on these two elements. Maximum times it has been asked. In case of chromium, 24 means argon 18, 4s1, 3d5. In case of copper 29, it is argon 18, 4s1 and 3d10. Remember these electronic configuration, special electronic configuration of a chromium and a copper, you remember these two. And which of the following is a transition element? Sodium, boron, iron and calcium. 1 year it was asked. So, among sodium, boron, iron and calcium, which one of the following is a transition metal? Obviously, it is iron. Question may be asked on this type. Define transition metal. What are transition elements? The dBLOCK elements are called transition elements because the properties are intermediate between electropositive S block and P block. Their valence shell and the nearest inner shell are incomplete and they have partially filled d orbitals. Okay? And mention two characteristic property of transition metals. There are so many properties. Today you have discussed variable oxidation state, metallic character, ionization enthalpy and many other properties that will be discussed in the next class. What is the general electronic configuration transition metal? Transition metal, it has not asked 3D metal. Transition metal means N-1D 1 to 10 and Ns 1 to 2. Write down the electronic configuration of ferrous. Ferrous already I have explained. What will be the electronic configuration? Iron. First write down the electronic configuration of iron. Then you remove 2 electrons. It will be your argon 18 and your 3D. You see it will be 4s2, 3d6. So, it will be your 3d6. So, why copper exhibit variable valency? Because of the closure energy difference between 3d and 4s subshell. Thank you for watching till end. Thank you very much.